Hello everyone, greetings of the day. The authors and invited guests, welcome to the technical session 5C. Myself Prashi, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastics LLP, it is my great pleasure to welcome you to the 10th International Congress on Information and Communication Technology, ICICT 2025, London, United Kingdom. The 10th edition of this conference is being organized in a hybrid mode. The physical event was held yesterday in London, United Kingdom, and the virtual event is being held through Zoom from 19th to 21st of February 2025. I hope you will enjoy the knowledgeable and interactive session through the day. In this session, we have 6 presenters. Each presenter will be given 12 minutes for their presentations, 3 minutes for the question and answers. On the 10th minute, I will be raising a gentle reminder. There is another request to all the participants that you all stay connected to us till the closing remarks. If you have any queries or update, then you can write it to me in the chat box. Just before we start our session, I would like to introduce you all to our session chair, Dr. Meenakshi Sumit Arya. Dr. Meenakshi Sumit Arya is an experienced research expert with a notable background in the field of artificial intelligence and deep learning, possessing a diverse skill set, skilled in machine learning, big data analysis, algorithm, data structures, and C++ programming with PhD focus in computer science and engineering, established a strong educational foundation. Ma'am, we welcome you to the session today. Would you like to make any opening remarks or for our participants today?
Thank you so much, Prashi, for that wonderful introduction. Well, I have been a part of the ICICT conferences since a lot of years, and I always see that there is a lot of innovation that goes on here. Just 2 disclaimers, please stick to the timeline that has been already mentioned by Prashi. And to the audiences, let's be interactive during the session so that we gain a lot of insights from what people are presenting. And to the presenters, all the best for your presentations. Back to you, Prashi.
Thank you so much, ma'am. So now, without wasting any time, I would like to start with our presenters today. Our first presenter for this session is Emmanuel Shidber Eze, presenting the paper titled Blockchain-Enabled Smart Contract Adaptation in Infrastructure P Projects, Understanding the Driving Forces Within the TOE Framework. If you are available with us, I request you to kindly take over with your presentation, please. Mr. Emmanuel Eze. Do we have you here, Mr. Emmanuel Eze? If you're here, I request you to kindly take over with the presentation, please. Okay. Looks like we don't have Sir right now over here with us, so I'll take the next participant, our next presenter, Leo Thomas Ramirez, presenting their paper on the title Enhanced Aerial Scene Classification Through Convex Architectures and Channel Attention. If you are available with us, I request you to kindly take over with your presentation, please.
Thank you. Yes, I'm here.
Okay.
Yeah. I'm not allowed to share.
Yes, I request you to kindly share your presentation, please.
Okay. Just okay. I think you have my presentation, right?
Yes, so I can see your presentation. It is visible.
Thank you. Well, yes, I'm going to present the paper entitled Enhanced Aerial Scene Classification Through Complex Architectures and Channel Attention. First, we have an introduction. The first topic is aerial scene classification. It is a task that categorizes images or video frames from aerial perspectives into predefined classes, including land cover types like forest, rivers, and also land use categories such as urban areas or airports. And this is essential for applications like geospatial analysis, environmental monitoring, and disaster management. because it helps to better understand and manage land surfaces. On the screen, you have some examples of land cover and land use classes. Now, regarding the challenges in area listing classification, it has some important challenges, including complex scenes with multiple objects and intricate patterns, which make classification harder. Moreover, while deep learning and convolutional neural networks have improved feature extraction, they may still struggle to capture global relationships. Transformers, as we know, have addressed this, and these are much better than CNNs, but are more computationally demanding. And additionally, one important point here is that training high-performing models requires large annotated datasets, which can be costly and difficult to obtain, especially for aerial imagery. Now, in light of the mentioned challenges, we explore the use of Cognex architecture for aliasing classification, which is a CNN with a design inspired by the transformers, while maintaining the efficiency of traditional CNNs. And to enhance the feature representation, we add also a channel attention between the structure and the classifier, recalibrating the importance of each channel and potentially improving classification performance. Now I'm going to talk about a little bit about the Cognex. As I told you, it's a CNN with transformer-inspired modifications. It was developed by Facebook researchers, and it is constructed based on the ResNet 50, incorporating several modifications. Some of these are a multi-stage design that processes features at different resolutions, I mean, basically multi-scale, allowing better capture of both local and global patterns. The use of the inverted bottleneck, as you know, expands first the channels and then you compress the channels, improving the feature representation while reducing computational cost. They also apply large kernels 7 by 7 instead of 3 by 3, capturing broader spatial relationships without significantly increasing complexity. They use the GELU activation instead of the rectified linear unit because it provides smooth gradient updates and improves optimization. And finally, they use layer normalization instead of batch normalization, reducing the batch dependency and improving consistency across all batch sizes. And thanks to these modifications, the Cognex has shown itself to outperform both traditional CNNs and other transformers like Swin or the data efficient transformer in image classification, and that's why we chose it to explore for its use in IRLSing classification. Now, channel attention. When we want channel attention, before that, it's important just to mention an attention mechanism, as it's in simple terms helps neural networks to focus on the most relevant features, whether in space, time, or across different channels. And in this case, in this work, the channel attention specifically focuses on featured channels. It assigns importance to each featured channel, let's say amplifying the relevant ones and suppressing less useful ones to refine feature representation. Unlike the self-attention in transformers, it is computationally more efficient, so it allows improving feature representation or selection without adding significant complexity. And we can see that in this comparative table where we have the self, the channel, and the spatial attention. And we can see that overall, channel attention offers a more efficient alternative by focusing on per channel importance with lower complexity and memory costs compared to the self-attention, while spatial attention falls somewhere in between because it has all the pixels, right? Now, in this work, the channel attention use follows a design based on the squeeze and excitation mechanism is a simple one, and it operates in two stages. First, we have the squeeze phase or stage where the global average pooling compresses spatial dimensions, capturing global context per channel. Then the excitation phase where you have two fully connected layers to adjust the channel importance. And the first reduces the interdimensionality using a reduction factor, as you can see on in the figure, while the second restores it. The rectified linear unit introduces nonlinearity, and the signal function just normalizes and recalibrates the weights between 0 and 1. And then these weights rescale the input feature map, emphasizing the most relevant channels. Now revisiting a little bit the approach in detail, we integrate the channel attention into Cognex by placing the module after the four feature extraction stages it has, or the four blocks for feature extraction it has. This allows the model to recalibrate the channel importance before pulling by applying attention while all the spatial dimensions are intact. The model fully leverages all the spatial information to assign proper weights to each channel, right? And after the recalibration, we just apply the adaptive average pooling that reduces the spatial dimension, and the features are then passed to the classifier for the final prediction normal. Now, regarding the dataset and implementation, the dataset used in this work is the USIMERSE, which is a widely used benchmark for aliasing classification, and it contains 21 classes with 100 images per class. And regarding the implementation details, we can do two experiments, one using 50% of training data and another only with 20%. And this setup is chosen because it challenges the models in a data limited scenario, where only those capable of extracting the most relevant features will achieve strong performance. And similarly, the training was limited only to 20 epochs to evaluate the model's ability to quickly extract relevant features and perform well under a short training regime. Finally, the training was conducted using Adam as of the optimizer, gross entropy as the loss function, and a batch size of 64 for all the models we use for comparison. We run them into using NVIDIA GPUs of 14 gigabytes. Now, regarding the results, the table on the screen shows the evaluation performance for 50% training data. And as we can see, the Cognex with channel attention does not have the shortest training or inference times. However, it achieves a notable improvement in accuracy, reaching 90% with a large model, and also near to the 90% in F1 scores, outperforming not only the baseline versions, I mean the Cognex without channel attention, but also other models like ResNet and Swing Transformer. And it's also important to highlight that other variants such as the Cognex base and the Cognex small with channel attention surpass 89% in accuracy, remaining basically superior to most other models. Sorry. Okay. Now, to analyze the results of this experiment more in detail, I present the confusion matrices of three of the best models. The Cognex large with channel attention, we see that this model correctly classifies a higher percentage of instances than the other models in certain classes, such as the Reaper that I have highlighted, when it reaches 72% compared to the 64% of Cognex without channel attention and 58% of Swing Transformer. And similarly, in other categories like Mobile Home Park, it correctly classifies 94% of the instances, outperforming the 86 percent achieved by the other models. Now, regarding the next experiment, the table shows the evaluation of the model strength with only 20% of the data, and as expected, overall performance drops, of course, because we have less data. But Cognex models with channel attention still lead the results, still have good results. Specifically, the Cognex based with channel attention achieves 77.14% of accuracy, more than 75% in F1 score, which is the highest among all the models. Once again, outperforming the ResNet and especially transformers that don't surpass 70% of accuracy. That said, it's important also to mention that Cognitive channel attention is not the fastest in training and inference, as we saw also in the previous experiment. However, the times are not excessively slow, so this position these models as viable options for practical applications. And moving to the confusion matrices, context-based channel attention, we can see that excels by correctly classifying 100% of instances in 6 classes, as I have highlighted. The agricultural, baseball diamond, chaparral forest, mobile, home park, and overpass outperforming the other models with fewer perfect predictions. As we can see in the comics without channel attention, we have less perfect predictions, and the transformers we only have 2 classes. It also shows slight improvements, but are improvements overall in categories like sparse residential and runway, which basically, despite the expected drop performance due to the limited training data, the cognites with channel attention remains superior to the other models. So overall, the experiments consider the reaffirm the viability of cognites, and we confirm that this is like the important change or addition of the channel attention. The cognites is good for IRLS classification. Finally, the conclusions we saw this work explored the integration of the channel attention model into the cognates for earlier classification. We evaluate the performance under 2 training regimes, 50% and 20% of the data set, while limiting to by 20 epochs the training to assess model efficacy and efficiency. The results shows that cognites with channel attention outperforms its baseline versions. Another models also like ResNet or Swing Transformer, which in accuracy is up to 90%, as we saw with 50% of training data. And even in constrained settings, or like 20% of training data, it also maintains strong results, demonstrating robustness in data limited scenarios, right? And future work could explore alternative attention mechanisms to assess the impact on the context, and additionally expand the evaluation to other data sets will help to determine the model generalization under more variable scenarios. And that's all. Thank you for listening.
Thank you for presentation, sir. Ma'am, do we have any questions for him?
We can just ask audience first if they have any questions. Anybody? Okay, if the audience do not have questions, then I have one question for you, Leo. A wonderful presentation, and it's a very novel topic that picked up. So I just wanted to understand, was there a comparative done? As you said, that channel attention is like it's a superior technology compared to the individual attention that we talk about in transformers. So is there some kind of a comparative that you have done between the channel attention, and if you do not, if you like take an overall attention, how does that vary? Is there a comparison like that done in AC?
So I didn't hear well, but I understood that you are asking if I made comparisons between different attentions, right? Okay.
Yes. Yes.
Okay. For this work, I have to say, I did it, but I did not use them because for space constraints, basically. But yeah, I did it. I did it. Like maybe in expanded version, I could pull that results, but yeah, I did it. Yeah, especially in training and inference, the times get higher, and also there are no like significant improvements using, for example, the classical spatial attention, because the training with in our experiments at least are specifically focused on limited data. So in this scenario, we saw that there are no significant improvements. So that's why we choose like presenting and using the channel attention in this case. Yeah.
Okay. And what was the size of data set that you had chosen, and was it annotated by your team, or was it like you did not mention a complete description about your data, like how many data points and what was the a complete description of the data.
The exact number, yeah, the split that you maybe I didn't mention because for time, but yeah, the split in 50% training was about 1,000 images, and in the 20% 420 images. So yeah, that's all.
Okay, because I just got like 100 images per class. So that's 21 into 100. That's the amount of data set that you are talking about, right?
Yeah, yeah.
Okay, awesome. Thank you so
Thank you.
much, Leo. Thank you.
Thank you. Now we'll take up on our next presenter. Our next presenter is Hamda R.H. El Abbasi, presenting their paper on the title Geospatial and Temporal Analysis of Hadith Narrators. If you are available with us, I request you to kindly take over with your presentation, please.
Yes, can you hear me?
Yes, sir, we can hear you.
Thank you very much. Can you see my slides?
Yes, sir, it is visible.
Alright. Okay, so I believe it's afternoon in London, but good day to everyone. My name is Hamad Al Absi. I'm from Hamad bin Khalifa University in Qatar, and together with my co-authors from Hamad bin Khalifa University as well as from Qatar University, I would like to present this paper to you, which is about geospatial and temporal analysis of hadith narrator. So this will be the outline of this presentation. This is a research that is relevant to the Islamic teachings or the Islamic religion. So in Islam, there are two main sources of teachings. One of them is the Holy Quran that was revealed by God to Prophet Muhammad, and the other one is the Hadith, which is basically the sayings, actions, and approvals, basically the teachings of Prophet Muhammad, peace be upon him. So Hadith has been collected, all of the teachings of Prophet Muhammad has been collected by scholars, I think around 200 years after his death. And these collections are well known as the six books. One of the famous one of them is the Sahih Bukhari, which was collected by the Imam Bukhari. So Imam Bukhari basically, what he did is he traveled a lot, looking for the teachings of Prophet Muhammad, and he made sure that he verified that these teachings, which he collected them into hadiths or ahadith, are basically verified. And one main thing to verify these hadiths is to look into the narrators or the chain of narrators and how the teachings were transmitted from one person to another across different generations. So one single hadith can look like this. So there are two parts. The chain of narrators, those who narrated and transmitted the hadith from one to another, starting from the person who witnessed or listened to the specific teaching from Prophet Muhammad, up to the last person who Imam Bukhari listened to or reported this teaching from. And the second part of the hadith is the text or the actual teaching of the Prophet. Now, this study looks into analyzing the narrator's movement. They started, or during the time of Prophet Muhammad, those who listened or observed or took the teachings from him were actually either living in Mecca or in Medina, currently in Saudi Arabia. But during the transmission, the narrators have moved from Mecca and Medina, currently in Saudi Arabia, to other places in the world. So what we are doing in this study is to analyze the movements and uncovering patterns of the narrator's travel, and hopefully, or what we did is basically highlighting regions that are that have or regions of where these transmitters or narrators have come from. Okay. The other thing that we did is basically leveraging the data that we have. We also created another set of verification, which is using their the date of birth or the date of death of these narrators, and looking on whether or not they have at some point met during their lifetime, as well as using the locations that are in the dataset. So this study is part of a bigger project, which is about visual exploration of hadith narrators, where we collected, where we have this application that you can find in the App Store for iPad that arrange the narrators across 12 generations from the time of Prophet Muhammad up to 200 years after his death. So these narrators are, as you can see in this picture or in this screenshot of the application, of the actual application, they are arranged in concentric circles. Each circle represents a generation. So what we are doing in this study, in this paper, is linked to this project. So first, we utilized a data in Kaggle about hadith narrators, which have around 24,000 data or 24,000 narrators. Each narrator has a lot of information, such as a unique key, the name, the grade, the generation, whether he was from the first generation, the second, or the third, and so on. The information about his death or birth dates, and the locations the locations of their birth or their death, or places or where they stay. Okay, so out of this 24,000 data, we created a subset of narrators that appear in the book of Sahih Bukhari. Okay, so we removed unnecessary columns such as the teachers of narrators and their students, their spouses, their children, and so on. We created columns for latitude and longitude of these locations that appeared in the dataset. We used the Hijri dates, which is according to the Islamic calendar, for the birth date, and adding, this is significant because we added a negative sign for the narrators that were born before the starting of the Hijri calendar, which is basically marked the migration of Prophet Muhammad from Mecca to Medina, currently in Saudi Arabia. Now, as it's the case with a lot of data sets, there are a lot of missing data, but we tried as much as we could to fill in these missing data using or by looking at some of the trusted websites that are specialized in the science of hadith. So out of 24,000, we ended up with 8,000 plus hadiths, narrators. And out of these 8,000, we used only 1,300 that appeared in the Sahih Bukhari book. What we did later on, we used kernel density estimation to create heat maps of the geographical locations of the narrators. We studied the distribution of the birth, stay, and death locations, and we created a KDE plots. We also created timelines for the narrators and those who are narrated from for a specific hadiths, in order to add an additional way to verify that they have met during their lifetime. So this plot shows the KDE heat map across 12 generations. So as you can see, if we start from generation 1, the concentration of the narrators were mainly in Mecca and Medina in Saudi Arabia, and there were a little bit of movement towards Basra in Iraq or Damascus in Syria currently. And as we move across the generations from one generation to another, we can notice that there is a movement that was basically concentrated or moved, or the transmitters or the narrators have moved or were shifted from a concentration in Mecca and Medina across places like Iraq, as well as later on, as you can see, starting generation 8 or 7, towards Central Asia, Iran, Turkmenistan, as well as Afghanistan and so on. And there were some people or some narrators who actually appeared in some places in North Africa. So this shows that at the early Islamic history, the narrators were concentrated in Mecca and Medina, but later on they moved to Iraq across cities like Asfahan or Nishapur in Iran. And then later on they moved into, or they appeared in other cities like Permiz in Turkmenistan or Afghanistan, as well as some places in the north. The other part of this project was creating a timeline analysis for each single hadith. So in Sahih Bukhari, we have around 7,300 hadiths. So these are two examples of how the timeline will help into verifying that the people of a specific hadith, for example, in this on the left side, we have hadith number 6,874. We can see that starting from Aisha to Abu Bakr, we can see that there has been, she has met the second person who took a teaching from her, that he took it from the Prophet, and then the third person met also the second person, and so on. We also tried to visualize their locations on the map. So as you can see, the first three narrators of this hadith most probably met in Medina, in Saudi Arabia, and the other or the last two, they most probably met somewhere in Iraq or Iran. So this also helps into finding places where they could have met and visualize it on the map. The second example on the right side shows another example of another hadith, but here you can see that we have missing data. For example, for the first one, Abdullah bin Mughaffal, we only have his death date, but we don't know his birth date. The same thing goes for the second narrator. So these are some of the challenges that we can find in this data set, but we tried as much as possible to fill in these missing values.
Sorry
But
to
all in
disturb
all,
you, sir, but we have crossed the 10-minute criteria. I request you to kindly wind up as soon as possible.
yes, actually, the next slide is basically the conclusion. So this study integrated the historical data from the literature of science of hadith and tried to use modern tools to explore the movement and relationships between different hadith narrators. The study provides insight into the travel patterns of hadith narrators across different regions. We also demonstrated how narrators could have met during their lifetime and at which locations. The last part will be integrated into our currently available Al-Ahadith application, which is available in the App Store. So thank you very much for listening. And if you have any questions, please let me know, or you can email one of our corresponding authors that you can see in this slide. So thank you very much.
Thank you, sir. Ma'am, do we have any questions for sir?
I just had a query. Yeah, as in, what are the algorithms that you have used here? Because I don't see like neither is amount of data too much that it's a challenging problem, nor is the the kind of analysis that you're trying to make too challenging. It's like you have a specific corpus of data and you exactly know what is expected out of it. So in the world of like, let's say, large language models, why did you not try using a open source model to just get the, get the spatial information or build graphs? I think the most obvious solution would have been to create a graph of relationships or use some kind of a social network mapping to understand a relationship and map the relationships between narratives. So
Yes.
what is the approach that you've taken? Because I somehow couldn't get the approach. Yeah.
Yeah, for this paper, we just use a simple kernel density estimation to visualize a heat map for the location. Only that. But we had an early paper in 2020 which we used social analysis.
Okay. So this is just a density-based estimation
Just estimation.
that we are using to understand. But how do you how does density-based estimation give you the temporal information about at what point in time who was where?
We just use it for the locations, as you can see from this slide. For the timeline, we use just a simple plot to find out. Yeah.
That's what I got. Is that density-based estimation will not give you the temporal information.
Yes, exactly. That was different.
Thank you. This was a very interesting topic. In fact, I Googled what exactly does this mean. So congratulations on the work.
Thank you so much.
Thank you so much, sir. Now we'll go on to our next presenter. Our next presenter is Emmanuel Shirabri Eze, presenting their paper on the title Blockchain-Enabled Smart Contract Adoption in Infrastructure PPP Projects, Understanding the Driving Forces within the TOE Framework. If you are available with us, I request you to kindly take over with your presentation, please. Are you here available with us? I can see sir is trying to chat with us in the chat box. I have unmuted you as per your request. We cannot hear you, is maybe because of some network issues. I request you to kindly please work upon it, and we'll just take the other presenters right now, if possible. Okay. Thank you. So, as sir is not able to join us in, we'll just go to the next presenter, Jonathan Brast, so presenting the paper on the title Join the video's description from multiple sources. If you are available with us, I request you to kindly take over the presentation, please.
Well, thank you for the opportunity, and I guess I will. Let me share my. Okay, I have to re-click because you were still sharing, and let me share the screen. Allow this, and hopefully you should see my screen right now. So
yes, that's visible.
Yeah, thank you for letting us present our paper on video description. So just for the outline, I will shortly introduce you to video description and kind of like the ideas we have on it. Then we will talk about our audio and video to text pipelines, talking about joining the data and the summarization and comparison of models, obviously. We were not training our own model. We are more in the, basically, the idea is to take existing models and look into how to integrate them and how to evaluate them. So let's think about videos for a moment. I mean, we are in there is a video right now. This, for example, is a video from a public talk. And you can see different sources of information in there. Yeah? So if you want to summarize the video, where does the information actually come from? Yeah, and you can see here and maybe listen to several different information sources in there. There's maybe text in the image. There might be an image that has to be interpreted. There's might be sound, music, and obviously there's speech, which is one main way of communicating information as humans. If there are also events like things changing, for example, an image of a car and an image of a car slightly moved to the left, it's a moving car. So this is also something that might be useful to interpret in there. So now that we have these different sources of information, there's obviously the question on what kind of different videos are there that we might want to describe in there. So we have different video genres. And for example, here in these three screenshots on the bottom, you see different kinds. On the left one is the kind of like famous E8 camera from the Apollo mission. And it's like original data. So it's a documentation video itself, like the image itself is the data. But there might also be stuff like a purpose that transports information, as I do to you right now, hopefully. and there might be entertainment purposes. Yeah, so this also informs somehow or that or which information is present. Kind of like, is it in the audio? Is it more speech? Is it music? Is there no audio at all? And in the video itself, is it an animated video, or are there people in there? All these different things, all these different kind of like descriptions, all these different information sources, we want to basically look into in videos. And that's also where we kind of like how we collected our videos to basically span over a range of different videos and video types with different purposes to generate summaries out of them and make them more accessible, make them discoverable. So the obvious architecture for this is, well, you take a video file, you put it into an audio pipeline, you put it into a video pipeline, and then you try to join it again into a summary. And the interesting thing in here is that the video file itself, it contains video and audio, yeah, but the common data of different models, or the common data format of different models, is in the end text, yeah, which is kind of like this whole LLM revolution thing. There is that we can now have text as this unstructured data format that we can use in different forms and from completely different models in there. In the audio pipeline itself, we have two different tasks in there where we take the audio data when we do audio classification on it. For example, recognizing sounds, recognizing screaming, bottles falling, car noises, stuff like this. And also the other big thing, obviously, in sound is speech. Yeah, because speech, as I already said, is kind of like the main way we convey information as humans. The problem with the speech recognition in this in here is speech recognition models have this kind of like tendency to hallucinate when you put anything in that is not really speech. So there's a diarization step in first where we look into is there anybody speaking at all, and kind of like time box in recognize the speech or detect the speech before we put it into the recognition software. So this already cuts up the audio into smaller chunks in there, as you can see here. For the video pipeline, it basically looks similar. A video, because we kind of like had different ranges of length of video, like the longest was like 4 hours and 5 minutes long, that we used was, and so you want a scene detection. Yeah, you want to cut it into smaller pieces so it's more manageable for the video language model, like this multimodal language model in there. So we cut the scenes into, or cut the video into scenes and feed them separately into the video LLM. So how would the data look like for now? Yeah, for example, here we have an example at a certain time point in a video, in a YouTube video. You can see on the side with the text, like both red highlights are from that exact time point in there. But you can see like in black other outputs for previous scenes, for example. And we have in here, for as an example, the whisper model as the text or the speech-to-text translation model, and LongVA as the video analysis, where you can also see like it says the video begins because we feed it into it like only the scenes, although it's not really at the beginning of the video, but kind of like you get the basic idea of this unstructured text. But also, if you now imagine this for our video, you kind of like, or even a shorter thing like an hour or half an hour or something like this, there are many scenes in there, and so the description gets kind of long. So in the summary pipeline takes now this long list of descriptions and optionally pre-processes it. I will talk to it before I, anyway, optionally pre-process it and then put it into a large language model that generates a summary. The pre-processing we thought was necessary because there's lots of redundant information in there, and we wanted to kind of like reduce it a little bit. Yeah, so take different chunks, make it smaller. The thing about this is, yeah, that kind of didn't work out so well. So we had better results, or at least usable results, when we used some long context things like long T5 or long former or GPT-4o. But then the problem was like long former, for example, long T5 had not the format that we wanted of the summary, which we just fixed by taking a small language model and saying, okay, here you have some output, please reformat it in another way. So, which models did we use? Yeah, for diarization, speaker diarization, Whisper, we knew from previous projects that we want to do like open source, like speech recognition, just use Whisper. YAMNet for the audio classification. And for example, here in the video description, you see like 3 models that we then evaluated a little bit more, and also some that we threw out because the results were very fast, detectable as not really usable. Also, in summary models, long T5 and GPT-4o worked. Short summary didn't work at all, and but we could put a smaller formatting model behind it. We then did some human evaluation on the video model selection. So this is kind of like German grades. 1 is the best, 5 is the worst, and the average grade is not so good, but at least we get a winner, yeah? From taking 45 scenes and ranking them and giving them basically grades and looking for correctness, we see that Qwen2VL outperformed all the other 2 models, and kind of like there were also models that didn't work at all. In the evaluation phase, like for the complete summary, we use UniEval, which is a language model-based evaluation metric, and basically it asks the probability for a language model to say yes to the question, is this summary or if this is a text and this is a summary, is the summary coherent, yes or no? Please give me the probability of this. It's a kind of evaluation metric. You may look it up. It's in our paper, or we referenced it in our paper. And also the different things that we did here is we tried like with the pre-processing step, trying to shrink the data that goes into the summary, and also speech only, and basically the whole pipeline. And you can see like in the speech-driven things, like speech only in GPT doesn't really isn't that worse than having the video data in there, but obviously in kind of like silent film, it doesn't work out so well. Okay, so as a recap, we had the audio pipeline, we used Whisper there, we had the video pipeline, best one was Qwen2VL, and GPT-4o, the best in the summary pipeline, so we get a summary out of it. Yeah, so let me give you some final remarks on it, what you can take out from this. So first of all, it's kind of possible, or is this task possible using only pre-trained models, but it's better if you use actually speech to text. Yeah, and on poor visual narratives, it sometimes forgets the narrative. That's not really a thing that language models are good in interpreting, like the story-driven things in there. Also, as I said, audio transcription is useful, and text recognition might augment it a little bit, but not so much. For you, if you work with textual data, long context windows are useful, better than trying to shrink it down from multiple chunks. And if your format doesn't look like you want to, yeah, just do a post-processing step, which is easier than trying to fine-tune your model. I'll finish in a bit. So different models can be joined into, like with text as this common format, and that's, as I said, the thing that we really want to drive home there is also that text is this universal format that different models can then speak and can interchange it. So that's interesting. I mean, it's not new anymore, but it's newish, kind of like in the last, wasn't there 5 years ago. So that's our paper, and yeah, hopefully you can get something out of it, and I was able to interest you in it a little bit. Yeah.
Congratulations, Jonathan. Awesome work. I have a couple of questions because I work on multimedia data. So
Yes.
my first question, like, what is the size of media that you're analyzing? Is it typically social media data that you're analyzing, or what is the length of videos that you are using?
So I mean, there were like these 4-hour YouTube videos. We also had like the complete film, The Matrix from 1999. I guess you remember, it's a cool film. in it, but also smaller videos. For example, Big Buck Bunny is a Blender video that has no speech at all and is just visual. So it's more like we try to get a good overview over the different types of videos. So it's not really a data set and more a collection of videos that we thought were representative of these different classes we described in the beginning.
Okay. So are you dealing with multiple languages, or is it just English content that you are dealing
We
with?
only did it in English right now. I mean, obviously, multi-language models sometimes are slightly worse. The interesting thing in here is that kind of like it's plug and play a little bit because text is common in there. I guess you could put a translation model in there as text is universal, but it seems like English is an even more universal language than other languages in there. I mean, yeah, but no, we didn't do
Right.
it.
So I presume you must be using the small version of Whisper or maybe Tiny, because you don't need to then go into Turbo or something which multilingual support.
Yeah.
Yeah. Okay. Yeah, I just also wanted to know, you mentioned about YAMNet. So YAMNet, if I'm not wrong, it has around 21 classes of audio classification. So are you using all those 21 classes, or have you kind of fine-tuned it for the number of classes that you want to extract by the end of your,
No,
are you?
I mean, we are using it as basically just a text attention. I actually would have to refer to Francisco if he's there if we use all of the classes. But basically, the thing is we try to map it to text, and so this detail is not a thing that I know right now. But we try to map it to text to get it universally in there. So it's not really about having these different, for example, probabilities of different classes, but more here's a text description of what happened auditively there in there. So it's kind of like usable by the summary model. Then, as I said, text as a human or a language as universal data is kind of like the central thing.
Gotcha. Yeah, one last question, so that will cover the entire pipeline. Now, you spoke about Quen 2. So are you using the 7 billion or 70 billion model? Because there's a significant amount of difference in the summary that you get depending on what is the size of the model. So which one are you using?
I think we were using the 70 million model, but I think we might have tried both, and I guess we went with the 70 billion in the end, but yeah.
We used the 7.1 only.
Use the 7.1?
Yeah,
So,
because my personal experience is 70 billion doesn't give that good a summary as 7 billion does. That's my personal experience. So I would not dump a heavier model onto my system just because it has got more number. Excellent work. I mean, I'm super impressed. This is something which the world is moving on to. Yeah, awesome work. Thank you.
Private author in there, you just corrected me.
Thank you.
Thank you so much. We have Mr. Emmanuel saying that he is now able to operate his PC better. So, sir, if you're available with us, I request you to kindly take over with your presentation, please. Are you available with us, sir?
Yes.
Yes.
Okay. I'm trying to share, and it's telling me the host isn't allowing multiple presenters for sharing. I don't know.
Please try again, sir. Now it might not do that.
Yeah. Can you see my screen?
Yes, sir. Your screen is visible to us.
Okay. Thank you very much. The title of my paper is Blockchain Enables Smart Contracts Adoption in Infrastructure PPP Projects, Understanding the driving forces within the technology, organization, and environmental framework. I'm presenting this paper on behalf of the authors. And my presentation is arranged in this order: research background and problem, the research methodology adopted, analysis and results, and then conclusion. Public-private partnership is an agreement between the public, that is the government, and the private individual, where they come together to share in the risk and benefits of providing critical infrastructure for public use. And then it's because of the importance of this project delivery approach, it has become a universal model for delivering different infrastructure projects in any conceivable sector. And over the years, it has experienced growth in different countries. According to World Bank record, investment in PPP in 2023 alone amounted to 86 billion US dollars. And the number of projects keep on increasing year after year. However, despite the growth in the developmental, the usage and developmental impact of PPP across nation, a large number of projects has suffered costs and time overruns. There has been reports of failures, terminations, and remunicipalization of projects. For instance, there's this report where over 1,500 cases, a record of 1,500 cases of remunicipalized projects that spans about 56 countries. And then this in both developed and developing countries. For instance, UK is one of the leading markets, or one of the most developed PPP markets, and the rate of termination of PPP projects in the UK is higher than the World Bank average of 5.4, while that of the UK is 6.8. Okay, so and then the losses for UK alone, the losses to public funds as a result of the failures of PPP projects is over 27 million pounds. And this amount is equivalent, this amount is enough to build over 1,500 new secondary schools for over 1.9 million pupils across the UK. And you can see a breakdown of projects, a breakdown of countries, the number of projects, and the breakdown in terms of remunicipalization, the sectors where you have more of these projects failing, or where these projects have failed. And what are the causes? You have issues of defiance in contracts obligations. You have poor data management. You have there's lack of transparency as a result of corruption, accountability issues, and monitoring. Value for money is hardly achieved. One of the key principles or objective of a PPP is value for money, and when it's not achieved, that's a key sign of a key indicator for failure. There is poor service quality, and the issue of payment and mismanagement of finances also coming, and a lot of the contractors or even the private experts, they take advantage of in an opportunistic manner. So blockchain and smart contracts are promises to address some of these drawbacks. Some of these drawbacks that PPP projects or contract experience, because it has unique characteristics that can mitigate some of these factors that are responsible for failures of PPP, and then it helps in building that building that relationship, keeping the stakeholders in that long-term relationship for the entire period of the project. And then it helps in it is a technology enabler for higher private sector participation in the provision of economic and social infrastructure. You can see some of the attributes or characteristics of blockchain-enabled smart contract, or directly I call it smart contract. It increases efficiency, better infrastructure asset liquidity, better transparency. You have data traceability and auditability, transfer of value and trust. So the capacity to offer this technology in PPP is as a result of the decentralized trust that it creates. It is scalable, it is immutable, and it helps maintain the relationship between the private and public sector throughout the duration of the project. Now, there are a lot of studies about on digitalization of PPP projects. You know, a lot of researchers and academics have carried out research to see how to use technology to mitigate some of the problems confronting the traditional paper-centric PPP projects. A lot of them are based on BIM. While BIM has its own limitation, it is centralized. It doesn't bring in that. It doesn't provide that trust and transparency because data can be manipulated or tampered with. So PPP studies on blockchain adoption in PPP, they are limited. You can see some of them here. None of these studies focused on the drivers or the factors that could influence the adoption of a blockchain in PPP or smart contract in PPP. And most of them are based on qualitative approach. You can see also the one that uses design science approach and all that. So, and then furthermore, these existing studies, none of them considered any of the technology adoption frameworks in their studies. So this topic or the aim of this study is to examine the potential drivers of blockchain-enabled smart contract adoption in infrastructure PPP projects. Now, those factors are within the TOE framework. This is a TOE framework with the variables or the indicators that were examined or assessed under each of the constructs. And then with H1, H2, H3 representing the hypothesis for the study. The methodology, the study adopted used questionnaire through snowball sampling techniques to collect data from participants in the industry, PPP expert, technology experts as well, and even government agencies. A total of 97 samples were collected and analyzed using various these analysis techniques displayed on the slide. So this is the research flow chart. There are once a potential respondent meets the survey criteria, he responds, he submits his consent and respond. Otherwise, it goes back to sampling. The analysis of the respondent background information shows that the data or the respondents cut across academics and industry, government, private, and the multilateral organizations, and they have acceptable level of experience in PPP as well as the industry. And you can also see the geographical distribution. Though most of the samples or participants were from the European continent, and none are from South America. The analysis of the drivers using relative importance index showed that the compatibility with existing contracting system or systems or technology in the organization is ranked first, followed by complexity of the technology, and then next is the relative advantage it offers. For the correlation analysis, the technological factors has the greatest impact on the intention, or has the greatest influence on the stakeholders' behavior to adopt smart contracts, and this is followed by organizational factors and then environmental factors. What are the implications of these studies? There are a few studies that have adopted quantitative techniques, especially the use of a survey method like questionnaire to study the adoption of a blockchain-enabled smart contracts in the construction industry. So this study represents a critical contribution, or contributes significantly to existing knowledge. And it also leveraged the TOE framework and developed a smart contract adoption model to examine PPP stakeholders' adoption behavior. It's also another contribution to literature because the use of TOE framework is yet to be utilized it has not been utilized in previous studies. In terms of practical implication, the study promotes the utilization of PPP projects, particularly as it improves transparency and information immutability, which helps to instill trust in the parties. The technology drivers have higher correlation and show very high significance, which also shows the organization where to channel in resources more in order to get this technology implemented. And then it also serves as an input to government and policymakers. They will be equipped with information on what driver to focus their resources on. Conclusion: the assess factors we are found to be highly significant and have the potential to influence stakeholders' decision to adopt smart contract in PPP. The technology component has the most influential, has the most influence most, has the most influence on stakeholders' decision to adopt PPP, followed by organizational factor and environmental factors. The construct for the TOE framework showed a strong correlation with the intention to adopt smart contract in PPP. So this is the conclusion of this study. And then, okay. Yeah, thank you for listening.
Thank you, sir. Ma'am, do we have any questions for sir?
Yeah, wonderful presentation, Emmanuel. So I just wanted to understand that when we integrate blockchain technology in PPP projects, so how can it be scaled across different countries with varying levels of, let's say, digital infrastructure and regulatory environments? So would you call your methodology a generic methodology, or is it specific to the country that you belong to?
Yes, it's a study that has its own. This study has a limitation. You can see the sample size is small, and then data were based on the experience of individual and not specific to any country. So it's not a it may have developed a model, but it's not a generic model that should be adopted by a different country. So yeah, it's not a generic model.
Yeah,
So it's a limitation.
Yeah, like what specific steps or policy adjustments do you need in your country to support widespread adoption of smart contracts? Because these, like the smart contracts, are typically based on trust and transparency among all stakeholders. So are those constraints also considered here, or you are just trying to build the system first and then ensure that those policies are, made which augment the system?
Yeah, one of the greatest limitation or factors to be considered is the legal and regulatory requirements, which is a major problem at present. There is no, most countries do not have those regulations. Yes, and then even where they have them, especially from developing countries, the enforcement is not there. So it's still a major issue. It's still a major issue.
Because that remains a major constraint when implementing blockchain. Thank you so much. Wonderful presentation.
I appreciate it. Thank you.
Thank you so much. Now we'll go on to our next presenter. Our next presenter is AGHR Guraj, presenting the paper on the title Optimized Edge AI Framework with Image Processing from Speed Prediction in Semi-Automated Electric Vehicles. If you are available with us, I request you to kindly take over with the presentation, please. Mr. Guraj?
Hello, hope I'm audible and
Yes, you're audible, sir.
I shared my screen. Can you see my screen?
Yes, we can.
The presentation mode, right? Okay. Okay. So hello everyone. So I'm excited to present my work on optimized AI framework with image processing for speed prediction in semi-automated electric vehicles. So let me start with the domain that I worked on. So the Internet of Everything is revolutionized industries by connecting people, data, things, and process. So one significant application here is the intelligent transportation system, which aim to improve traffic management, enhance safety, and optimize efficiency through technologies like AI and machine learning. So within ITS, so connected autonomous vehicles play a crucial role using advanced AI to perform driving tasks under human supervision or without the supervision. So traditionally, these ITS relied on image processing techniques like edge detection and feature extraction to enhance traffic system. However, advancements in deep learning have enabled more accurate solutions. So the reason why I'm predicting this vehicle speed, so the predicting vehicle controller parameters is essential for connected autonomous vehicles, especially in electric vehicles, which rely on advanced electronic systems for their operation. So unlike in traditional vehicles that uses complex mechanical linkages, so EV uses ECUs, the electronic control units, to manage critical functions like acceleration and braking. So these systems operate with precise electronic signals, so that will allow much more streamlined mechanism compared to the other vehicle types. So when it comes to the speed prediction, so accurate speed prediction enables drivers or automated systems to anticipate changes in traffic and adapt gradual deceleration strategies in avoiding sudden braking. So this approach again gives the energy efficiency as well. So it does so by optimizing the use of regenerative braking systems, which contains in the electronic vehicles. So electronic vehicles kinetic energy will be converted into the storage battery power. So predictive control like this ensures the smooth operations and contributes to the overall sustainability of the electric vehicles. So when it comes to the why I'm going for a semi-autonomous vehicle is when it comes to the fully autonomous vehicle, there itself contains some issues. I mean challenges like still one major issue is the dominance of human-driven vehicles on our roads, coupled with the unpredictability behavior of human drivers, which makes seamlessly integrate difficult. So therefore, that is one challenge in current domain. And then the high cost of advanced sensor systems required in those fully autonomous systems again creates a financial barrier as well. Another thing is reliable network communication infrastructure in many regions. There is the lack of the infrastructure is also an issue when it comes to fully autonomous vehicles. And then when it comes to real-time prediction, yeah, which is ideal, but again, it comes with an own set of challenges. Like it requires continuous video streaming to the in-vehicle hardware. Therefore, we need advanced in-vehicle hardware as well. Therefore, it will increases the expenses and contradict the goal of the electric vehicle, which is lightweight one. So again, over the network, the bandwidth issues, the network interruptions also could be there. Therefore, rather than going for real-time prediction, we are going for an time gap prediction, like 30 seconds interval gap. So because of this reason, this work is developing an AI framework focused on 30-second speed prediction for urban transportation. And our objective is to assess machine learning and deep learning models for speed prediction and to analyze the image compression over trade-offs, and then the measure system performance as well. So let me take you through the process flow. So how the process flow has been done. So every 30 seconds, the vehicle camera is captured an image of its surroundings. And then the interval is specifically chosen to suit the semi-autonomous nature of the vehicle. So where a human pilot is present for immediate maneuvers, but for routine tasks like speed prediction can takes over after a short delay. So then the image is captured to the edge server. So different compression levels are applied during the testing to evaluate their impact on bandwidth usage and processing time. And then once the image is received for this server, again we have the it undergoes the object detection and speed prediction. So the predator speed is then sent back to the vehicle through the same wireless network. So vehicle will receive the vehicle speed and it can adjust parameters accordingly. So when it comes to the network issues or network interruptions, we have implemented the offline model concept. So we have implemented it within the vehicle itself as a reliable backup. So that's there. And then for this work, I have been utilized the ICICT Open Datasets, which was released on 2023. So this is a multimodal dataset created specifically for autonomous driven research. So this dataset is not very widely used, so therefore I use this dataset. So this in this dataset, I specifically focused on the frames category, and for certain countries only that has the most data. And then I extracted the relevant details of the from the image that are required for the speed prediction, and then handle the imbalances as well. So I use the Google Colab and NVIDIA that has the NVIDIA T4 GPU for the processing. And then to simulate client and edge servers, I use Docker containers. And to model the offline model concept, I use an VirtualBox for simulation. So for each country's dataset, I use for the object detection part, I use DeepLab v3-50 model. And then we have the speed prediction task. I wanted to test like machine learning models and deep learning models, which are performs better. Therefore, I utilize these models. And then the requirement is to use that in the edge. So these models should be lightweight, that has the fast inference times and low latency that can be used in the edge. And here are the evaluation matrices that I used here. So when it comes to results, the first one is the evaluation of machine learning and deep learning models. So the reason why machine learning models outperform here, because the structured nature of the dataset, because the simplicity of the task as well. So that's why this here we have found that the machine learning models outperform here. Next, we analyze the how image compression impacts the transmission time. So I have been incorporate the image transmission. So if you can see when we apply the compression more, the image size is reduced. That means the bandwidth is less, and then the time is also less. So finally, we tested the offline model concept. So it has the inference time of 0.03 seconds with these resources. So those were the results. So when it comes to limitation, I have been utilized from that ICICT Open dataset, and then for 5 countries of data. So we are thinking of expanding the dataset to incorporate the speed prediction into here. And then we have utilized a current system used the fixed 30-second interval. So this can be utilized as solid baseline, but we are thinking of expanding it for a dynamic interval. And then we have the scalability issue. So we are thinking of incorporating federated learning concepts here as a distributed nature to make servers as distributed. And then network communication should be also validated with other technologies, and we have to compare that as well. So those are the future work in this research. So these are the frame conclusions. So the study demonstrated framework that can be utilized in the Edge. So, but by integrating this HAI, so the system offers practical solutions for semi-automated public transportation systems. So that's my work. So thank you very much for listening.
Thank you, sir. Ma'am, do we have any questions for him?
Yeah. Hi, Himan. I would like to congratulate you for finishing your presentation. My question would be that how does the choice of image compression technique actually influence your prediction accuracy and latency under varying network conditions? Like I couldn't place the relationship between image compression and how is it affecting prediction?
The reason is we have the image is captured from the vehicle, right? So the image should be sent to a server for the prediction. So we have to think about like the bandwidth, and we need the faster inference time. Therefore, we have to think about like sending the original image or the better one. The more the image compression happens, we have compared as well the accuracy of the image as well. So the reason is the bandwidth and the faster time we need for the prediction.
But I don't see your images being like they are not in megabytes. The image that you're talking about
Yeah. So
are in KBs, and with 5G bandwidth available today, I don't think that is that big a concern as is the quality of image. Also,
yeah.
is there a reason that you have like there's a 30-second gap in capturing subsequent images, because that's a huge gap in 30 seconds. God
Yes.
forbid a crash can happen in a second.
Yeah.
So, like, what logic behind sending a frame after every 30 seconds? Because in 30
The
seconds, the
reason,
car moves a significant distance, right?
yeah, that's true. The reason because what I have as a benchmark, that's why I mentioned in the future work, I'm going to reduce the time gap as well. So as a start, what I did was to get a 30-second interval to send the image first and then to receive the results back. I predicted that 30 seconds enough, because we are predicting the speed. I mean, you mentioned that the immediate conditions can happen, but the here semi-automated nature, we have the human driver as well. So that's why I'm going for a 30-second ahead interval, 30-second ahead prediction.
So you are predicting the speed that the driver should maintain 30 seconds
30
later,
second
right?
ahead. Yes, that's true.
What is the variance that you get in the predictions? For instance, like is there a graph which shows how the trajectory of a vehicle is predicted as per the system which you are designing? Have you plotted it in the form of a time series?
Right now, no, but I have the results of I mean the prediction results are there.
Because it would be very important to understand, as when you say that you are using a machine learning, like a random forest or just the models which you have used are very primitive. And then if you are
Yes.
having live data where you are trying to use these models to make a predictive inference, like having it predicted on the basis of what has seen earlier might not be the best possible solution. And if you analyze the trajectories of what is predicted and what was the speed with which actually the vehicle was driving, that can give you an insight about where the model needs to be tweaked or how do you need to change your methodology of what you are doing right
Yes.
now.
Yes, that's true.
Yeah. Yeah. It's very essential to at least plot the trajectory. Well done. Good job. Thank you, Himant.
Thank you for the feedback. Yeah.
Thank you, ma'am. Now we'll call up the last presenter for our session. Our last presenter is Yung Kyung Shin, presenting a paper on the title Semantic Landscape of Legal Lexicons, unpacking medical decision-making controversies. I request you to kindly take over with your presentation, please, if you're available with us.
Hi everyone, I'm Hazel Kim, and due to a very urgent personal issue, Dr. Shin was not able to attend this conference. So as a first author, I'm filling in for her. So I'm sorry for all the convenience, and I would like to present our paper. Let me share the screen first. Okay. Do you see my presentation slides clearly?
Yes, ma'am, this is visible.
Okay, thank you. So our paper is titled When Medicine Meets the Law, Computational Insights into Legal Disputes over Medical Decision Making. And I'm here for my team at Department of Sociology, Korea University. And I would like to mention that unlike the formal presentations, which showcased amazing engineering and technical contributions, our research is mainly a social science research, but we are applying computational methods as a new innovative way to do the social science research. First, to briefly provide an abstract of our research, we empirically examine the semantic trajectories of the legal medical conflict. So our primary goal was to unveil the lexical structures and diversity of lawsuit verdicts related to medical decision, especially the doctor-patient communication. And we do so using the auto-crawled text data, legal verdict text data, and we apply some state-of-the-art topic modeling methods and semantic network analysis. So to begin with, I would like to first briefly introduce what is shared decision making in medicine, SDM, which is the key core concept of our research. It is a collaborative process in which patients and medical professionals deliberate on and make medical decisions together. So the core concepts that are constituting shared decision-making in medicine are duty of care, duty to explain, and right to self-determination. So the first two duties, duty of care and duty to explain, is duties of medical professionals, clinicians, physicians, and the right to self-determination is right of patients to determine and express their preferences on which kind of treatment they would receive. And the strength of SDM perspective in medical procedures is that improves treatment adherence of the patients and better prognosis. And it is also, it shows that the using SDM in the medical process increases patient satisfactions and quality of life. But even though we know that there's those kind of strengths, the institutional adoption and practical application of SDM is still at an early stage at most of the countries. So our research team aimed to understand what are the current barriers and current state of SDM adoption in early stage countries, but the biggest obstacle was that there was not a well-curated data set to understand the current state of SDM adoption. So for the final option, we believe that medical lawsuits and verdicts could be a great empirical source to observe and understand the current state of existing medical conflicts and how the medical decision-making is now occurring in the practical environments, and what kinds of obstacles related to SDM are hindering the actual practical adoptions. So we thought so because ineffective or improper medical communication potentially escalates into lawsuits. And medical verdict data provides a very detailed about how the medical conflicts were initiated, developed, and escalated into legal conflicts. And also the judges assess the degree to which clinicians' duties and patients' rights were fulfilled. So we thought that it is a good empirical source to understand the current state of SDM. So our goal was to unveil the semantic landscape of medical conflicts using medical legal verdict data. So the four sub goals we had was to identify critical themes of medical legal conflicts, tracing how the core concepts of STM, the duty of care, duty to explain, and right to self-determination, those three key concepts have been contextualized in legal discourses. And actually, it's very important in STM perspective that those three key concepts, the two duties and right of patients, are well connected to each other. So we wanted to also see whether they are really corresponding to each other and well connected in the legal discourses. And we also aim to clarify the barriers of STM adoption and implementation. And also we wanted to test whether the medical verdict data can actually have heuristic utility that we expected as empirical source to understand the current state of medical conflicts and STM adoption. So for the data, is actually the screen here is written in Korean, so you may not understand, but it is actually the example of publicly available verdict data provided by South Korean government. And actually, it is a verdict about a medical maltreatment lawsuit, and it is a verdict data provided by the Supreme Court. So we thought that South Korea could be a great example case to understand the current state of STM for two reasons. First, the Korea has a long history of medical legal lawsuits, so we thought that there might be an ample amount of data set we could delve into. And second, although Korea has a high quality of medical systems, the adoption of STM is still at an early stage. So due to those two reasons, we thought that South Korea could be a great sample case for to understand the current state of STM adoption in this research. So we automatically crawl the publicly available legal verdict data using the word patient as a search keyword through the Supreme Court of Korea's legal information database. And after filtering and manual screening, we selected 205 unrelevant documents for our final dataset because the initially crawled 1,022 data some of them were relevant to STM, but some of them actually didn't have any connection to STM problems, so we excluded them, exclude the irrelevant documents, and for the final corpus, we only included 251 court verdicts. And for the analysis methodologies, we employed two main methodologies. So the first one was the neural topic modeling. For the neural topic modeling, we used BERT topic with Legal BERT, a pre-trained language model that is specialized for the legal domain to capture the contextual semantics of the words and sentences within our corpus and classify the documents by their main topics. And after applying topic modeling to our corpus set, we conducted semantic network analysis for each topic to understand the actual semantic landscape and how the key STM concepts are contextualized within each corpus. So we considered each word as node, and we identified co-occurrences within a predefined window, which was verdict document, the whole verdict document in our research, as the tie connecting the nodes. And for the cluster detection, we used Luvian community detection algorithm because it is most widely used for the large data set. And for the representation of the networks, we only included top 500 words based on their co-occurrence frequencies for the visual representation of the semantic network analysis. So let me first provide the historical semantic network of the entire final corpus as our first result. So this historical semantic network places each word when its cumulative occurrence reaches 20% of its total frequency. So it displays the words in longitudinal sequence. So this network reveals that the lexical diversity of legal medical verdicts have expanded dramatically over time. And the increasing complexity of the semantic network structures might suggest that patient-doctor communication issues now cover a much broader range of medical services and medical conflicts and practices compared to the past. And for the topic modeling results, we identified two major themes. So the first topic was about liability of the medical professionals. So this topic was explained by keywords, including negligence, surgery, treatment, medical death, procedure, hospital, patient circumstances. And as you could see from the example sentence, this topic is mainly about whether the treatment choice of the clinician was actually proper and whether they integrated patients' preferences. And the second topic, which we titled financial compensation, was represented by keywords amount, pay, expenses, damages. And as you could see from the example sentence, it is more focusing on, compared to topic one, is more focusing on financial restitution rather than the clinical practices. So for to understand what kind of semantic landscapes are actually there for each topics, we conducted in-depth semantic network analysis for each topic identified from the topic modeling results. So this network is the semantic network we derived from topic one, from the documents that belongs to topic one. So when we take a closer look at the two specific clusters in which three key SDN concepts belong, in the left-hand side, I'm not sure you could see my cursor here. So on the left-hand side, it is in that cluster, it includes duty to explain and duty of care in a very small sized fonts. And in the right-hand side, you could see self-determination, which was another key concept of SDM. So
Sorry to
here,
disturb you, ma'am, but we have exceeded the limit criteria of 10 minutes. I request you to kindly wind up as soon as possible.
okay, thank you for the note. So let me just briefly wrap up this session. So we could see that even though from the SDM perspective, the connection of the duty of the medical professionals and the right of patients are really important, you could see that those duties and rights of patients are belongs to the two separate clusters, which means that they are not really interconnected within the legal discourses. And in the topic two network, we could also see the same trend. So we could see that regardless of the topic, the duties and patients' rights are not really closely interconnected, which it means that even though the three key SDN concepts exist and have developed in the legal discourses, their interactions or interconnectedness have not really developed within the institutional discourses yet. So that was the biggest finding of our research. So briefly wrap up, the lexical diversity in medical conflicts has expanded over time. And the rhetorics of the right of patients to medical self-determination are not closely tied to the professional responsibility to explain and care. And three key concepts of SDM were even more minimally represented when medical verdicts primarily dealt with financial compensation. So there are several limitations, but the most important contribution or research is that even though there are SDN concepts exist in the legal discourses, their meaning clusters are decoupled, which means the SDN perspective is not really reflected in the legal discourses yet. So for more questions, you may email me or Ngyang anytime, and I'm happy to answer your questions anytime. Thank you.
Thank you so much. Ma'am, do we have any questions for them?
Wow. Wonderful. It was one of the different topics that I heard today. So congratulations at Kim. Is it that you have tried to build, graph relations among the various nodes which you have, and what kind of interactions are there between multiple nodes which form your graphs?
I'm not sure I understand your question correctly, but was it about that the meaning of the interactions between the nodes in the networks?
Yes, yes.
So the interaction of the nodes, so the tie means that the two words have occurred has appeared in the same document. So it means that they are building a semantic meaning together. So the co-occurrences or the type of the network is very important when we understand the existence of interaction between the semantic units, the words. But actually the duties, the terms that are explaining the duties of medical professionals and the words that are explaining the rights of the patients, those two set of words and terms were not co-appearing enough in our legal discourse dataset, which means that SDM perspectives focus on interconnectedness is still not yet reflected in actual practical institutionalization.
So have you all considered doing some kind of entity normalization here, because multiple words which are coming into picture might mean the same?
Right. That's a great point. So we try to, I think that comes from the translation process from Korean to English, because I
Right.
think we've done the entity recognition and summarization process, pre-processing with Korean text first. And then for this conference, we translated them into English. And actually some Korean words are differently expressed in Korean, but actually when we translate them in English, they are expressed the same words. So I think the problem is coming from that one, I guess.
Okay, great job done. Thank you.
Thank you.
Thank you so much. With this, we come to the end of the session. I sincerely thank you, our authors, for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough, and we thank you for being the part of our 10th version and all the other previous 9 versions of this conference. We will be happy to have you in the 11th version in 2026. All the presenters will be getting their digital certifications through email within 2 working days. Further, all the papers have been already forwarded to the Springer. The publication will be live within 6 months. Kindly cooperate with the team of ICICT 2025. I also thank our session chair, Dr. Meenakshi. Ma'am, we have a token for you. Oh, hold on 1 second. We like to thank Dr. Meenakshi for chairing the session. A token of appreciation to the chair on behalf of Team ICICT 2025 and Global Knowledge Research Foundation and partners. Thank you so much for your valuable presence, ma'am. Would you like to make any closing remarks?
Yeah, thank you so much. It was wonderful to hear so many good presentations, such a diverse range of research that people are doing. And it's always good to get feedback from peers in such conferences. And I look forward to seeing the authors with their, enhanced work in the next conference as well. And I wish everybody all the best. Thank you.
Thank you so much, ma'am. I just request all of you all to kindly switch on your cameras just to have a quick snapshot of this virtual session that we have attended just now. Requesting all of the authors and the presenters, kindly please switch on your cameras for a quick snapshot. Thank you so much.
Thank you.
We can log out. Thank you so much.